CMOS RF integrated circuits. We are discussing bandwidth estimation techniques, and in today's lecture we are going to continue with the method of open circuit time constants. Basically, I want to give you some ideas of how to do a design based on back of the envelope hand calculations using the open circuit time constants. So, in our earlier lecture, we were working with a MOSFET, and I had asked you to assume the following small signal parameters to start with. So, let us say GM was 10 millisiemens, GMB was 1 millisiemens, RDS was 2 kilo ohms, then I had CGS of 200 femtofarads, CGD of 50 femtofarads, C drain to body of 100 femtofarads, and C source to body of 150 femtofarads. These were the numbers we started from. I chose nice round numbers so that I can do convenient hand calculations. Anyway, doesn't really matter. These numbers also are not very unrealistic. They are quite nice, realistic numbers. All right, and then if you recall, yes, the previous lecture, you will see that we started off from this as our design. We wanted RL of 2 kilo ohms and a load capacitance of 1 picofarad. We wanted to drive a load capacitance of 1 picofarad, right. So, we started from this as our design, and then we saw that we got a horrible bandwidth. We saw that we got a bandwidth of only 84 megahertz, right. This was our first cut design. From the first cut, we said that our bandwidth is 84 megahertz, and the culprit was the load capacitor. Tau L was the culprit, right. So, because tau L was the culprit, why was tau L the culprit? You can't escape the load capacitor, it is 1 picofarad. Now, the problem was that along with the load capacitor, at that point you see an impedance of 1 kilo ohm, 2 kilo ohm parallel 2 kilo ohm, that was 1 kilo ohm, that was causing the problems, right. I did not want to see 1 kilo ohm, I wanted to see something much lower resistance. If you would drive this huge capacitor with a low impedance, then you would get a much smaller open circuit time constant for that particular one. So, this was the reasoning, and my second cut design had a buffer. This was my second cut design. I put a buffer over there, basically to reduce the impedance seen, to reduce the resistance seen by the 1 picofarad load capacitor. I put a buffer over there, and from a resistance of 1 kilo ohm, I started seeing a resistance of where is it, 90 ohms, right, and the corresponding tau was only 90 picoseconds in my calculation, right, and this result, the total tau was 1089 picoseconds. It resulted in a bandwidth of 146 megahertz. Not bad, could be better. We want gigahertz, right? Could be better. We probably want a much wider bandwidth than 146 megahertz. So, in that case, what do you identify as the culprit? Let us say you want much better bandwidth than 146 megahertz. What are you going to fix? Which is the largest tau over here? largest tau now is 600 picoseconds, corresponding to the gate to drain of device number 1, C gate to drain of device number 1. Now, C gate to drain of device number 1 was a small capacitor to start with. We are talking about this, right. It was a small capacitor to start with, but it seems to be resulting in a large time constant. Why? Why is C gate to drain resulting in a large time constant? What are you seeing over here? This is called something. This phenomenon is called Miller effect, right. So, it is as if C gate to drain is being multiplied by the gain of the device. I have a gain of 10 for my device, and the effective capacitance now for C gate to drain is something like 10 times 50 femtofarads. So, 500 femtofarads instead of 50. Now, that was bad news, that is really bad news, and that is basically what causes problems. So, what do we do? So, this was our first cut design, then we moved on to our second cut. Our second cut design had right. This was our second cut. And clearly, now the problem has been identified as this particular capacitance, and we need to fix this particular capacitance. How do we do that? So, how do you fix problems with Miller effect? How are you? What is the commonly used strategy? You use a cascode, right. A cascode or a common gate structure after the common source structure is what is going to fix the Miller effect problem. So, instead of my second cut design, what I would do is something like this. So, I have my source what is this? You are basically now seeing a low impedance looking in over there. You are looking into the source of a MOSFET that will show a low resistance, and as a result you are going to get a much lower gain from the first device. Then much lower gain means, what does much lower gain means? Much lower gain means that the Miller effect is now nullified or reduced substantially, right. This is basically the idea. How does the cascode work? The cascode, that's basically how you get the speed up, you get the bandwidth, you get a better bandwidth. The cascode, how it works is, you basically create a change in current. You are applying VGS across this device, you create a change in current. This change in current has nowhere to go but through the drain of the second device, and basically the gain that you see is this change in current times the output impedance looking into the drain of the second device. Now, the output impedance looking into the drain of the second device is going to be what you see looking above, which is that resistor or whatever you have over there, and what you see looking below. What you see looking below is a much larger resistance, right. You recall the two formulae, all right. the two formulae for analog circuits. Formula number 1. This is formula number 1. Please keep this at the back of your mind. And formula number 2 okay. So, these two formulae are all important. So, keep these two in mind. So, basically when you look into the drain of the device, you are going to use this particular formula, and effectively you are multiplying whatever you see below the source by a quantity which is GMRDS1, which is the gain of the cascoded device. So, over here the impedance that you see is RDS times GMRDS. It is a large number. Okay. That is how the cascode works, just as a reminder. Anyway, let us do this properly. So, we have got 2 kilo ohm here, 1 kilo ohm here, CL equal to 1 picofarad, and what are the different capacitors that we have? For device number 1, we have CGS 1, we have C gate to drain 1, C source to body of device number 1 is irrelevant because both sides are at ground, drain to body of device number 1 is relevant, right. Now, device number 2, we have gate to source of device number 2, we have source to body of device number 2, drain to body of device number 2 is irrelevant because both sides are at ground, gate to drain of device number 2. Okay. Now, device number 3, gate to source of device number 3, then gate to drain of device number 3, drain to body of device number 3, and source to body of device number 3. All right. So, these are all the capacitors and of course, CL. These are all the time constants that we have to compute. So, let us do it systematically, one step at a time. So, CGS 1, let us call it tau GS1. What is the resistance you see? The resistance you see is 1 kilo ohm. So, you pull out that particular capacitor, kill everything else and see what is the resistance looking in from those two terminals. So, you see 1 kilo. So, 1 kilo ohm times CGS 1 is 200 picoseconds. Okay. Then tau gate to drain of 1. So, what are you going to do? You are going to kill all the other capacitors, replace that particular one by a voltage source and see what is the impedance that voltage source is, what is the resistance that voltage source is seeing. Now, this is a problematic circuit because both it is a floating voltage source. So, what you would want to do is you would want to re-reference it to one of the terminals, right. That is what you would prefer doing. So, we are going to redraw it as follows. So, first of all, what is the resistance that you see looking upwards? The resistance that you see looking upwards is given by one of our two formulae. So, it is 2 kilo ohms plus 2 kilo ohms divided by 1 plus GM times RDS. Is it just GM or GM plus GMB? Should be GM plus GMB because those are coming in shunt with each other. Okay. So, that is the resistance that you see looking upwards. So, that happens to be, I have brought my calculator, about 174 ohms. Okay. So, keep this in mind. So, what we have got is something like this. And we want to apply a voltage source across gate and drain. Now, what I am suggesting that you do is instead of the ground being at the source, why don't I redraw this circuit with the ground at the gate? So, if I redraw the circuit with ground at the gate, then what I am going to be getting is something of this fashion. All right. And as soon as you put it in this fashion, then the impedance looking into this over here comes out from one of our two template formulae, and the impedance happens to be equal to GM. Will you be getting just GM or GM plus GMB? GM and GMB are coming in parallel to each other. So, you will be getting 11 millisiemens times RDS. RDS and 174 ohms are in shunt with each other. So, you get 2K in parallel with 174. This is where you are getting the advantage, right. This 174 is what is giving you the advantage, times 1 kilo ohm plus 1 kilo ohm plus 2K in parallel with 174. So 2K in parallel with 174 ohms is 160 ohms. So net what you get is something like 292 ohms or 2.9 kilo ohms, I am sorry, and the capacitance is 50 femtofarads. So from 600 picoseconds you have dropped to 146 picoseconds. Certainly you have done a good job. All right. Now the next one is CDB1. So CDB1, what do you see? You see 174 ohms looking upwards, you see 2 kilo ohms looking downwards. So you basically see 2K in parallel with 174 ohms, and that is 160 ohms. Okay. So that is your device number 1. Now let us work on device number 2. Device number 2, see source to body. Okay, I will continue over here. Source to body of the second device. So over here, if you look at that point, apply a voltage across source to body, what do you see? You are going to see the resistance presented by the source of M2, right? And the drain of M2 is connected to ground, not even to any resistor. So you basically use this template formula, ZD is 0. So RDS divided by 1 plus GM RDS. GM over here is the parallel combination of GM and GMB. It is the sum of those two. So you get 2K divided by 1 plus 11 millisiemens times 2K, right. So it's about 87 ohms. Picoseconds. What about the load? It will be the same computation. You will get about 87 picoseconds. Okay. So let me mark out whatever we have done. Okay. See gate to drain of the second device. let us do this particular one. See gate to drain of device number 2. What is the impedance presented at the gate of M2? What is the resistance presented at the gate of M2? Looking into the gate, of course, you see infinitely large resistance. Looking over here, you see 2 kilo ohms, and looking downwards into the drain of M3, you see a large resistor, whatever is the value. I have not written the value of that. So, looking downwards over here, you see a large resistance, and the template for that large resistance is once again given by one of your two formulae. It is now given by this particular formula, right. So, it is basically GM3 RDS3 times RDS1 plus RDS3 plus RDS1. Right. So, that is your resistance. So, you are basically going to see 2K times 11 millisiemens is 22K, I am sorry 22, factor of 22 times 2K is 44K, 46K, 48 kilo ohms in parallel with 2 kilo ohms, that should be about 2 kilo ohms, 1.92 kilo ohms. And the capacitance is 50 femtofarads. So, I basically get 96 picoseconds. All right. Now, the difficult one is CGS2. CGS2, once again you have to dereference the particular node, right. You have to refer to ground as the gate. Now, before doing that, you should remember that the impedance looking in over here is 48 kilo ohms, right. That is an important thing to remember. So, I am going to redraw my circuit to look like this. Of course, you have removed CL and all the other capacitors. Yeah, nothing else is there, right. And now you dereference this particular situation. You make the ground as the gate, make the gate as the ground, and that is going to mean that this is what I have got, right. And as soon as you have something like this, you again put it back to your template formula. It is amazing, it is really amazing. These two formulae are all that you need to do analog circuits with MOSFETs. These are the two formulae, period. Okay. So, once again you look back at your formula, which is RDS plus ZD divided by 1 plus GMRDS, and that's basically going to give you 2K plus 48K divided by 1 plus 2K times GM is going to be the parallel of GM and GMB, because they are in shunt with each other in this particular case. Whenever the source is not ground, GM and GMB are really in shunt with each other, right. Body is at ground. Okay. So, this is basically going to give me 50K divided by 23, it is about 2.2 kilo ohms. .430 picoseconds, that is a large number, that is a large number over here we have got, might have to worry about it later on. Okay. Now, that is as far as device number 2 is concerned. What about device number 3? Device number 3, I have got C drain to body 3, that is identical to C gate to drain 2. C gate to drain 2 saw 1.92 kilo ohms. Right, and then I have got source to body 3. Source to body of device number 3 is exactly the same as drain to body of device number 1. Drain to body of device number 1 saw 160 ohms. Then I have to worry about gate to source 3, which is also similar to source to body 3. Then I have to work on, so this is what I have done this, done this, done this. So, I have to work on C gate to drain 3, which is the same as drain to body 3. Right. So, I have computed all the time constants. What is the sum total of all the time constants? That is going to give me the total time constant. Then from there I will be able to compute the bandwidth. So, I have got 200 picoseconds from device number 1, and I have got 146 picoseconds from gate to drain of device number 1. I have got 16 picoseconds from drain to body of device number 1. Then what else have I got? I have got 13 picoseconds from source to body of device number 2, 87 picoseconds from the load. I have got 96 picoseconds from gate to drain of device number 2. I have got 430 picoseconds from gate to source of device number 2. I've got 192 picoseconds from drain to body of device number 3. I've got 24 picoseconds from source to body of device number 3, 32 picoseconds from gate to source of device number 3, and 96 picoseconds from gate to drain of device number 3. Net I have got 1332 picoseconds, which gives me a net bandwidth, 1 by tau is the bandwidth of 751 mega radians per second divided by 2 pi gives me 119 megahertz. Okay, it's actually worse than my previous design. It's worse than my previous design. And why is it worse? Because I've got a problem over here. I've got gate to source of device number 2, which has escalated the situation. Gate to source of device number 2 has escalated the situation. It's very strange though. Okay, we get what we get. This is a little strange. It's not right. It's not right. What is not right is this 48 kilo ohms. Looking in over here, I can't ever see 48 kilo ohms. I see 48 kilo ohms in shunt with 2 kilo ohms. All right. So that was the mistake that I made, and as a result, I get wrong answers. Yeah, so that was surprising. That was surprising. Please make this correction. So 430 femtofarads is not right. You get 30 picoseconds, not 430 picoseconds. All right. So once again, let me do the totaling. 96 pico, and then I've got 32 pico, and then I've got 24 pico, then I've got 192 pico, then I've got 34 pico, okay, that's better. So my new sum total is 936 picoseconds. So, we have a problem, we do not have a problem, we have done better than the previous case. The previous case was 1089 picoseconds. Now, I have improved, not much, marginally, but I have improved to 936 picoseconds, which basically gives me a 1.07 gigaradians per second bandwidth, and convert that to hertz, I get 170 megahertz. Okay. So, from 146 I have improved to 170 megahertz. Not bad. It is not bad, could have been better. Now, which of these components do you identify as problems? So, 192 is a problem, looks big. $200 tau GS1, that is really the largest over here, 200 picoseconds. Everything else is a small quantity. The second largest is this 192 picoseconds, that is coming from drain to body of device number 3. So, possibly this could be my culprit, but this is definitely a culprit. So, gate to source of device number 1 is a culprit. How can we fix it? So, device number 1 should not be seeing such a large resistance. Right now, it is seeing 1 kilo ohm resistance. I should not be seeing such a large resistance. How do you fix it? You add a buffer stage, right? So, my next design could be something that looks like this. So, I have added a buffer in front of device number 1. All right. Now, computations as far as M3, M2 are concerned will all remain the same. Only things that will change now are CGS1, C gate to drain 1, right. See, drain to body of device number 1 is not going to change. So, I need not work again. Now, I have got to worry about a few new capacitors. I have got C gate to source of device number 4. I have got C gate to drain of device number 4. I have got C drain to body is irrelevant for device number 4. I have got C source to body of device number 4, which is going to come in shunt with gate to source of device number 1. So, these are the new things that I need to compute, all else remains the same. Okay, all the other taus are not going to be affected at all, right. So, this is my plan. Let me put a number here. Let us say I stick to my 2 kilo ohms resistance. All right, fine. So, let us do step by step. What is the resistance that CGD4 sees? the resistance that CGD4 is going to see is 1 kilo ohm, nothing else. So you are still stuck with that 50 picoseconds from there. What about CGS4? You are going to do some dereferencing, right? So CGS4, it's a system that looks like this. You have applied voltage across the gate to source junction. You are now going to say that let me call the gate as my ground instead of elsewhere. So I am going to call the gate as my ground, and I am going to look into the source to see what is the resistance that I see. Is this correct? That's okay? All right. Now, what do you see? This again falls into your template, right? You just have to modify the value of RDS. So you are basically going to see 2K parallel with 2K plus 1K divided by 1 plus GM plus GMB, that's 11 millisiemens times 2K. I am sorry, 1K. Right, and the result is basically going to be 2K divided by 12, that's about 166 ohms. So you see 33 picoseconds coming from CGS4. Then see source to body of device number 4. If I look at the source to body, the resistance presented by the source of device number 4, you see basically 2K looking downwards, and looking into device number 4 you see 1 by GM approximately, right, approximately 1 by GM. It's really 1 by GM plus GMB. It's really RDS by 1 plus GM plus GMB times RDS, right. Once again it's the same formula. So it's 2K divided by 1 plus 11 millisiemens times 2K, right. This whole thing in shunt with 2K. So it's about 87 ohms in parallel with 2K. So 83 ohms. Okay. Similarly, gate to source of device number 1 will also see the same thing. So, it's suddenly become all small numbers. Picoseconds. What remains is gate to drain of device number 1. Gate to drain of device number 1, you've got to remember that looking this way you are really seeing 83 ohms. Looking upwards, I've forgotten my numbers. I think it was 174 ohms, that is correct. So, this is how we had computed for gate to drain of device number 1, and now instead of this 1K over here, what we have got is 83 ohms. So, that is the resistance that you see looking in. So, you are basically going to see GM, that is 11 millisiemens over here, GM in shunt with GMB, times RDS is 174 ohms shunt with 2K, times 83 ohms plus 83 plus 174 in parallel with 2K. So, that is the impedance, that is the resistance that you are going to see. So, let me just do the computation. So, this is 160 ohms. So, you basically see 389 ohms. So, the resistance has dropped even further. So, you end up with something like 19 picoseconds. So, these are my changes, these are the changed values, all the other values remain the same as before. The device number 4, these come in addition, right. So, let me do my sum total. I have got 50 pico, 33 pico, I have got 12.5 pico, I have got 17 pico, and I have got 19 pico. 131 pico in total. Device number 3 remains identical, device number 2 remains identical. So, let me keep adding. Gate to drain of device number 2 remains the same. Load remains the same. Source to body of device number 2 remains the same. Gate to source of device number 1 has already been accounted for. Gate to drain of device number 1 has already been accounted for. Drain to body of device number 1 is not really going to change. So my net tau has reduced to 721 picoseconds, and that is going to give me a bandwidth of 220 megahertz. So that's quite a jump. Okay, so basically this is how we use the method of open circuit time constants to determine the bandwidth to improve upon our design. If you further want to improve upon your design, then you have to take this as your culprit and work on it, right? You basically identify which is the culprit, work on it, improve the bandwidth. Then again you identify the culprit, work on it, improve the bandwidth, right? Now of course, in our method we assumed that the MOSFET has certain parameters. That's really not the case in general. You can vary the width, the length of the MOSFET, and that is going to also change the gate to source, gate to drain, etc. capacitances, right? And that is also one of the knobs that you can use to improve bandwidth for yourself. All right. So this is basically my method of open circuit time constants. The next part, we are going to discuss something which is the method of short circuit time constants. It's not a very great value, but I think it's important for us to know that too. Thank you.